Right. Okay. So yes, David, as I mentioned, don't be surprised if we interrupt you constantly.
Yeah, no worries. Yeah,
so-
I'll be anticipating that.
yes, and
So yeah, okay.
it'll be a very informal type presentation. So
All right, so I guess a little bit of an introduction for those who don't know me. I'm actually, so my name is David. I'm a third-year PhD student, actually going into fourth year now, at the Stats Department, University of Toronto. So this work is actually still quite preliminary, but I guess as Renee told me, like this is pretty much like a discussion type of thing. So I thought like it would be great to get some feedback and talk a little bit more about this. And I'm actually quite excited about this work. So what this is about is basically we're trying to construct a very principal integrated Bayesian model to infer the global cluster counts in ultra-diffuse galaxy using something called Mark-dependently thin point process. So this work is jointly done by my wonderful supervisors, of course, Gwen, everybody knows, and Patrick Brown and Bob Abraham. And also together with a bunch of my collaborators, Bill Harris, Josh, cannot be here, Sam Barrick, and Shani Danieli. Okay, so first of all, I guess what are ultra-diffuse galaxy? I think probably for most astronomers, I guess we all know. So for those who don't know, it's basically a class of extremely faint galaxies that were actually first detected in quite a massive number in the Coma cluster using the Dragonfly telescope by Peter Van Dukum at Yale and my supervisor, Bob Abraham, and back in 2015. So here's probably one of the most famous Dragonfly UDG ever discovered, Dragonfly 44. So this is basically what it looks like, and from an HSD image. And so why are these guys interesting? And the thing is, we have found that actually many UDGs have abundance of global clusters in them, but despite them being like extremely faint. And so, for example, the Dragonfly 44 I just shown, that actually has about, I think the current estimate is about 75 global clusters in them. But for comparison, like Milky Way has about 150. So, but the thing is, the Dragonfly 44 is 100 times fainter than the Milky Way. So what's going on over there? And there are also a couple of other UDGs that have abundance of global cluster in them. The DF2 in the NGC 1052 group is one. And one important use of global clusters in UDG, of course, is to infer its dark matter content. And actually for Dragonfly 44, for example, I think they actually used its global clusters to infer its dark matter is pretty much 99%. In terms of like its total mass. But there are a couple of issues. One big issue is that there has been quite a massive dispute on the actual global cluster counts. So one example of this is the DF2. And there are also a lot of issues on the existing method for how people actually count GCs and UDGs. So I guess this is going back to grade school.
Can I ask a quick question?
Yeah.
About UDGs themselves? Are they? I mean, they're diffuse, so I guess there is no known structure that can be discerned. So that means they're like ellipticals, or they're basically just one big cluster.
I think in terms of like morphology, I think it's pretty much just looks like a elliptical. That's what most UDGs look like. But yeah, I'm not sure if it's like big cluster or something. Like it's just like pretty much on an image. It's just like a blob of faint lights, and that was pretty much like in terms of morphology how they look like.
I mean, are they small in terms of mass?
Oh yeah.
Actually, it depends. Sometimes like some UDGs they found to be like similar to dwarf, but for Dragonfly 44, it's actually I think estimated to be about the same mass as Milky Way.
Oh,
Yeah.
wow. Okay.
Yeah, so they're really weird.
Hmm.
And the DF2, this one, it's even weirder. Like they also use, because this one is much closer, they use spectroscopy on their global cluster, and then they inferred that this galaxy has no dark matter.
Hmm.
So this one is pretty much all dark matter, and this one has zero dark matter. So they're really weird. And that's also why like a lot of people are just banging on them and trying to study what the hell is going on. But yeah, does that answer the question?
Yeah, thank you.
Okay.
Yes.
So yeah, like how do people actually like typically count global clusters in UDG? So I guess the first thing is what people usually do is they extract all the compact sources in an image, and then they just say, oh, these are pretty much like, you know, supposedly global cluster. But there's already issues over here. Like, how do you know for sure? And then the next thing they do is to basically draw an aperture. So usually, basically, this is just like drawing a circle around the center of a UDG, and then which is typically 1.5 times the effective radius of a UDG. And then they just count how many compact sources or supposedly global cluster within this radius. And what they usually assume is that this 1.5 effective radius is the half number radius for this for the GC system. So they would say, oh, outside of this radius, there's another half of the global cluster. So the total number is just double what you however many you counted within this aperture. But the next issue is there's the GCLF, so which is the global cluster luminosity function. So what happens with this is a lot of the times at really far distances, global cluster population are not fully observed because there's a detection limit on the telescope. So like the fainter end of the population of global cluster are basically like removed. You don't observe them. So what people usually do is, because like GCLF previous, like I think like nearly like half a century of study on GCLF is pretty much like solidify the fact that GCLF is pretty much universal. So like it's the same everywhere in the universe. So they basically just assume a fixed GCLF, and they just say, oh, like the detection limit is over here, and I know the GCLF is somewhere, which is basically a Gaussian distribution. And then they basically just say, oh, like the proportion of GC global cluster that are not observed is this much. So now I counted this many observed. So like the total is just, you know, the total divided by the proportion that you can observe within the GCLF. But there's also an issue with this, which I will talk about later on. And then lastly, they just do a background correction, which is just like
one quick question again about this GCLF.
Yeah.
I mean, you said it's Gaussian?
Yeah.
How narrow is the distribution?
Usually, if I remember it correctly, the typical, like the canonical GCLF that people usually adopt is like, I think the absolute magnitude in visible band, I think is like -7.5-ish, and then the dispersion, like standard deviation, is about 1 to 1.2.
Huh.
Yeah.
That is extremely narrow. And
yeah.
I guess it's so if you have any sort of problems when excess background or slightly larger distance, you're going to miss almost all of it, right? I mean, that's what happens. So like that's what happens when, like, that's a big problem when people do these kind of things. Like they a lot of times they just like take the canonical GCLF as the Bible, and then they just assume the fixed one, and then you will see like it just that assumption just like it can lead to a lot of problems. Okay. But yeah, and then the last step is basically the background correction. After you get this the GCLF corrected, people just grab another patch of sky where there's nothing over there, and then just like get an estimate of like how many global clusters there are in the background. So like background, that's basically intergalactic medium, and then you subtract that number from whatever previous estimate you have, and then that's your final estimate on the counts.
So obviously you can see there's a lot of issue with this kind of like traditional method. So of course, first of all, what exactly is a global cluster, right? Like we don't know. And what typically like GC expert does is basically to look at the color magnitude diagram, the CMD, and then they basically separate out a region within the CMD of point sources, and then say, okay, like global clusters should typically reside in this region, and then they just do a box cut. But that is also something like I'm not particularly fond of, and basically in this work I did something else. So I basically did a probabilistic classification of global cluster, but that's a little bit too much detail over there, so I'm not gonna talk about that too much. But and the second thing is the global cluster membership. So what this means is like when we get an image of global cluster, we don't exactly know which environment does this global cluster belong to. Does it belong to the background? Does it belong to the UDG? Does it belong to one of the nearby giant elliptical galaxy? Nobody knows. You can only know that by a spectroscopy, but like for most of the time, very large distance spectroscopy is like impossible. So, and yeah, the next thing is the go back to GCLF. So is it actually universal or no? If you fix the GCLF, what is the uncertainty associated with it? And what happens like if also like the GCF is actually not universal? So how do you deal with those? And then the next thing is basically there will be a lot of uncertainty associated with global cluster surrounding the detection limit of telescope. So what happens over here is that, of course, as I mentioned, like the proportion of global cluster that are too faint, that's getting removed. How do you probably account for those? And also there was another issue with the magnitude of global cluster, is that the actually measured globular cluster magnitudes, the uncertainty gets higher as you get closer to the detection limit of the telescope. So the measurement error over here in general is not considered in any of the previous study that I've known. And the thing is, it could lead to quite a bit of problem if you do not consider the measurement error. And the thing is that measurement error generally grows in an exponential fashion. So it might be worthwhile to actually consider them as well. And then the next thing is basically the correction of the global cluster at large radii. So as I said, this is basically aperture thing. Like when people generally assume the 1.5 effective radius for the aperture, is it actually 1.5 effective radius, or is there any kind of like variation? Like how do you account for the uncertainty? Like nobody really, thought about it more carefully. And then this next issue is crowding. Crowding is not that much of a problem for UDG because crowding generally happens in the core region of like supermassive giant ellipticals where there's thousands of GC clumped up together, and it's just like you could not tell one GC from another one. But the thing is that would not generally happen in UDGs. And but the thing is, like for completeness, I still consider it over here. And lastly, which is actually going back to the GCLF, is that for these two galaxies, so the DF2 and DF4 in the group NGC 1052, people actually found that these two UDGs have really weird GCLF. Their GCLF is, I think, estimated to be about 2 magnitude brighter than the canonical GCLF expected at their distance. And this basically caused a massive like shockwave in like GC community, and some people were saying, oh, like you guys did something wrong, like the distance is wrong or something like that. And but the other ones are, oh, maybe UDGs are indeed oddballs. Like we don't really know. So there's like quite a bit of dispute on this as well. So as we can, there's a last one, the probably the weirdest. A lot of these methods, they produce negative estimate on the GC counts. So yeah. So as you can see, like the previous method actually tried to address a lot of these issues, but the thing is, like they do it in a very fragmented way. And the method is also pretty ad hoc. And then there's a lot of uncertainty associated with the assumptions. And these uncertainty pretty much like they're not taken care of, like they cannot be taken care of sometimes. And although there are a couple of newer methods, more recently, one is by Amerisco and the other one is by Carlston. But both of these methods have their own flaws and did not address all of the issues just mentioned. So basically,
this negative estimates, I mean, are they just a consequence of background subtraction? I mean,
most of the time it is. Yes.
Okay.
And that's weird, right? Like you would not expect it because it's a count. Like the smallest count is 0. Like why would you get a negative? Right. That makes no sense, right? So basically there isn't really a like a principal unified method that deals with all this issue together. And basically in this book, this is what I've been trying to do. So I'm basically trying to do this through point process. So not going to go too much detail on like what point process are. But the main thing is that we want to model the intensity function of the point process, and which is basically the mean surface number density of globular clusters. And of course, the simplest model for point process is the homogeneous Poisson process with the constant intensity. And then if the intensity depends on the location or varies across space, then it is basically an inhomogeneous Poisson process, or IPP. And we basically want to model the GC point pattern as an IPP. But there's an issue. Not all the globular clusters are observed because some of them are like getting chopped off because of the detection limit. And so how do we deal with this? Well, the nice thing about point process is that there is actually a model that directly deals with this, which is the thin point process. So what this is actually just an operation that's being acted on a point process, which is basically just to randomly remove a bunch of points according to some probability. And that probability is also called the thinning probability. So what's good about this? Well, the good thing about this is that if the original point process is a Poisson process, and if the removal of the points are independently done to each of these points, then the resulting thin process is still a Poisson process. And the nicest thing about this is that if the original process has intensity lambda, and if the thinning probability is p, then the resulting thin process actually has intensity lambda time p.
But so isn't that true only if it's homogeneous? I mean, if you got
no, it's not just homogeneous. It could be inhomogeneous as well. Because your PS also depends on location as well, right? So but the thing is, this is true only for independent thinning. So like if this PS is acted upon, basically the removal of points on the is basically independent, like for each of the points. If that is true, then you have this, but it doesn't necessarily need to be homogeneous. It could be inhomogeneous as well. But yeah, but the problem with this type of basic thin process is that the thinning of globular cluster or removal of them usually depends on the magnitude. It does not usually depend on location. So this basic thinning process is not going to cut it. So what we want right now is another type of point process is called the mark point process. So this is basically just a extended type of point process where each point in the point process has some characteristic which we call mark attached to them. And the intensity function of a mark point process right now also gets extended. So right now the intensity depends on the location S and the mark at the same time. And so in our case, of course, the mark is basically going to be the magnitude of the globular clusters. And usually in terms of modeling, we will decompose this intensity into two parts. So it's basically a product of this lambda 0, which we call the ground process. So this is basically just the process or the intensity of the point process when there's no mark. And then this pi 0 is basically the mark distribution that may or may not depends on the location. So this is basically a probability density function for the mark. And in general, we just separately model the lambda 0 and pi 0 in terms of the actual modeling. And now this is the actual meat of the entire project, is the mark-dependently thin point process. So this is actually a framework originally proposed by Milimaki in 2009 in her thesis. So the main idea is to say, what if I like let the thinning operation to depend on the mark? But the problem with her work was that it was pretty much all theoretical. She provided some summary statistics, some simple estimators for the model, but there was no consideration of joint modeling of locations and marks, and there was no like full Bayesian inference conducted on some like real world complex problems. So I think as far as I know, this is pretty much like the first time ever like this has ever been done. And also we wanted to provide a little bit more like holistic view and provide some more insights on what this model framework actually is. So here's a little bit more detail about it. So as we've seen before, for the basic thin point process, we have a thinning probability that depends on location S. But right now, I basically introduce a new thinning probability, which I call the mark location thinning probability, that depends on both the location and the mark. And so what we want is to figure out what the intensity for this MTPP is. So it's basically also a marked point process. So if it's a marked point process, it could still be decomposed into a ground process and a mark distribution. But right now it's just all thin version. And we basically just want to figure out what each of these parts are so that we could do modeling. So for the thin mark distribution, so pi t, it is actually just a probability density that's obtained by applying this TSM, this mark location thinning probability, to the original mark distribution in a fashion like that's similar to truncation. So the thin mark distribution is basically given by this thing, which is basically just a simple truncation. And after that, we then want to figure out what this thing is. So this, of course, we know it's going to be a thin version of the original ground process, lambda 0. But we need to figure out what this thinning probability rho s is. And this rho s right now basically just depends on s. So that basically just means we need to marginalize out the effect of the mark m. So the rho s is basically just an expectation on TSM with respect to the original mark distribution. So it's basically just this integral. And then your thin ground process is basically original ground process multiplied by this rho s. And if you work out the kinks, you actually get this, the MTPP intensity is actually just the original intensity multiplied by this new thinning probability. So what this essentially is telling us is that this MTPP is actually nothing fancy. It is just a simple extension of the original thin point process where you have one extra dimension being extended to, which is the mark dimension. But yeah, so I figured this is pretty neat, and actually made us understood a lot more about what this thing actually is about. And so right now, after all that, we can actually talk about the models. So there are actually two models that I've done. So the first one is I'm assuming that each environment. So basically,
sorry, can I
yeah.
quick question? So
yeah.
One thing I don't quite understand is why do you need to do the thinning?
Oh, the thinning is because there are global cluster being removed.
Removed in the sense of detectability?
Because of their magnitudes, right? Because a lot of them global cluster are too faint and they're not going to get picked up by like the telescope. So these guys, you're not going to see them in like an image. But the thing is, doesn't mean,
so you're including the this detection, effectively this detection process as part of your model.
Yes.
Okay.
Yes. So,
This will make Shaoli very happy, I'm sure.
oh,
He keeps asking me to do that sort of thing. With
Yeah, that's nice. That's actually nice. Yeah.
yeah, and so yeah, there are two models I've constructed. So the first one is I'm assuming basically different GCLF. So what happens over here is that I'm assuming that depending on the environment, so for example, whether you're in intergalactic medium or you are in some kind of a galaxy, each of these environment, they can have different globular cluster luminosity function. So I'm not assuming they're the same. So what's going on? Okay, so the model basically goes like this. So the first, there's a like massive hierarchical Bayesian model. So the first layer is basically assuming that the observed point pattern is some inhomogeneous Poisson process with some intensity lambda. And this lambda is basically a superposition of the intensity of n different environments. So that basically leads to this big lambda is the sum of the intensity of a bunch of different environments. So these individual lambda m is basically one, is the intensity of globular cluster in one environment. And the magnitude of the globular cluster over here, given the location of the globular cluster and the intensity, I'm assuming it's some kind of mixture distribution. So the mixture distribution is mixing over all different environment. And this basically deals with the GC membership uncertainty. And through this way, like it's naturally accounted for. And so this PM over here is basically the membership probability that the ith globular cluster belong to the mth environment. And this new F over here, I will talk a little bit detail on how to get this thing, but this thing is basically the mark distribution for the magnitude in the mth environment. And then the PM actually has an explicit like formula, which is basically just the intensity in the mth environment divided by the total intensity. And the actual modeling of the intensity of each of the individual environment. So for lambda 1, I'm assuming this is basically the intergalactic medium globular cluster. So this is basically, I'm assuming it's a constant across space. So that's captured by this beta over here, which is basically a constant. And then PS is the crowding effect. But in our problem, I'm just going to assume PS is 1 because that basically represents the case there's no crowding. So you're going to detect everything, and that's not going to be removed due to crowding effect. And this psi F here is basically related to this new F, but you can just think of it as the proportion of globular cluster in this first environment that you're going to see or you can observe. And for the rest of the environment, they're basically just all galaxies. They could be UDGs, they could be dwarfs, they could be ellipticals, whatnot. So these are all just modeled by surface profile. And with 3 parameters of interest, so big N is basically the number of globular cluster in this environment or in this mth galaxy. So which is probably the most important parameter that we're interested in. And R is basically the GC system radius. And then little n is the surface index. PS is still the crowding effect. Psi F is still pretty much same as this Psi F over here, is basically the proportion of globular cluster that you could observe in this environment. And then, so this is the first model. The second model is making a different type of assumption, is I'm assuming that the GCRF is the same across different environment. So right now you can see this magnitude basically has one single distribution. Everything else is the same. So yeah, so there's a little bit of detail about what this new F is. So new F is basically the thin version of the mark distribution, and is basically just applying our formula that we just got from before. And there's also a little bit more stuff in over here. I'll talk about it a little bit later. And so the thinning mark location thinning probability over here, I'm just assuming it's a product of the crowding effect PS and FM. FM is basically the good old completeness fraction of point sources. So this is basically measuring how what is the proportion of point sources that we are going to detect in an astronomical image at a given magnitude M. So this is typically modeled by a logistic function and with parameter A and M0. So M0 is basically the 50% completeness limit. And these parameter A and M0, they're basically just determined by artificial fake star test. And so, yeah. And then this actual psi distribution over here. So this is the original Mark distribution, pi 0, without thinning, right? But this is not exactly the GCLF, because the actual GCLF is actually contaminated by the measurement error when we go down to the detection limit. So this psi distribution is basically a convolution between the true GCLF with mean mu and sigma square, which is the Gaussian distribution, convolved with another Gaussian distribution that basically describes the measurement error. And this measurement error is basically modeled by a exponential form. And this is these parameters still obtained by artificial fake star test. And so here are some results. So the data that we use is
quick question. So when you say artificial fake star test, that's just injection of a fake source into real data and then running through the process?
Yes. So basically just putting a bunch of like fake point sources into like an image and then like count how many, like what is the, so for example, what is the fraction of stars that you can detect at that magnitude.
Effectively, you've done this, Monte Carlo simulations and figured out what all these parameters are.
Something like that. Yes, I mean that's generally what people do in the GC community to determine these things. So are these
and this exponential measurement error. That's not just the statistical uncertainty, right? I mean, is that also detection process dependent?
Yeah, that's detection dependent. That's not statistical, because like this is basically the issue when this M true, so the true magnitude of your point sources, as it goes down to the detection limit, it basically goes, the measurement error basically goes like this. It just increases exponentially. Because as you go down to the detection limit, like your measurement basically gets closer to the sky background noise, and then that you just cannot like that noise is just like gets really big.
Right. I mean, this is sorry. Go ahead, Annette.
Yeah. I was just wondering because that's interesting. I never saw this type of measurement error in this application, so it's kind of a different concept.
Yeah, a lot of people don't consider it.
No, we do have the detection issues, right? And there is I mean, Vinay has this upper limit paper, which we were publishing 10 years, 15 years ago, maybe. But and there, the probabilities were changing, but we were not considering the exponential errors in that case. So it's
I don't think these are, I mean, so this is sort of codifying the Eddington bias somehow into the model directly, right? I mean, it's not really statistical error.
But it's an interesting way of putting it. I don't know if that's something which is commonly done in other fields than X-ray astronomy, but I don't know.
I've not seen this before, definitely.
Yeah, it's the first time I've seen it. Anyway, sorry, it's just exciting.
Yeah, it's cool because I don't think anybody, when they're doing like GCLF measurement, like they never really consider this a measurement error. They just use their measurement as the true magnitude and then just be done with it. But the thing is, like when this thing goes exponential, is that actually true? But yeah, so some results. So the data that we are using is the Piper survey by Harris et al. And so this is basically a HST survey targeting the Perseus galaxy cluster. And we got a bunch of GC candidates out of it. And the magnitude that we're considering is basically the I-band FA14 filter. So I'm just going to show one field of results, and because that's the only one I got at the moment. So this is the V7 ACS field. So over here, these black dots are basically globular clusters, and the scale is on the kiloparsec scale. And what's happening over here is these red triangles, these two red triangles are basically the location of two known UDGs. So I'm going to call this UDG the first UDG, this UDG smaller one, I'm going to call the second one. And the results that we got.
Oh, by the way, we can't see your cursor.
Oh, you can't see my cursor?
Yeah, in case you're pointing at them. So
okay, so what I meant is like the UDG at the top left is the first UDG, and the UDG at the bottom middle, that's the second UDG. Okay. So under model 1, so assuming the GCLF is different for different environment, so this is the posterior distribution for the number of globs in the two UDGs. So this is the first one, this is the second one. So the red lines are posterior mean. And then here are the results from the model 2. So assuming GCLF is universal across environment. So this is the first one, already a little bit different. And this is the second one. Oh, so second one over here, this red line is not actually posterior mean, this is posterior median, because this distribution is way too skewed. So posterior mean doesn't really make any sense. So what happened? Well, of course, GCLF happened. So here are the basically the posterior distribution of the mean of the GCLF, so the mu parameter, or as people in global cluster call it the turnover point. So this is the posterior for the mean of the GCLF for the first UDG, so about 26-ish in terms of the magnitude. And then this is the posterior for the second UDG. And you can see how massive a difference is. It's about 24-ish. And under the model 2, when there's one single GCLF, it's even fainter. It's 26.5-ish at the posterior mean. So basically what happened over here is that those basically the global cluster in the second UDG, they actually have there are about 3 of them, and then their magnitude is all about 24-ish. And that's basically about 2 magnitude higher than the majority of the global cluster in that field. So what happened with model 2 is that if you're assuming, basically the model 2 is saying, oh, if you're assuming the GCLF is the same across all environment, then these 3 global cluster, it's near impossible for like a single environment with a mean of about, let's say, 26-ish, right? Because this is 26.5-ish mean at GCLF, to produce 3 global cluster that's like 2.5 magnitude brighter than this mean. It's near impossible to do that. So what happens is that the model is basically pushing those 3 global cluster into the background, into the majority of the population. So because when you have a bigger population, it's more likely to produce those 3 global clusters that's like 2.5 magnitude brighter. So basically the model is saying, like, those 3 global clusters does not belong to that UDG, actually. It just belongs to the background. So that's basically what happened. And as you can see, that's basically what will happen when you have these kind of assumption and assuming that GCLF is universal. And here are some comparison with some summary statistics about our estimates. And there was actually a previous study done on the estimates, but that is more using the traditional method. And their method is generally using like maximum likelihood, so it's not Bayesian. So all these are pretty much like non-existent. So as you can see for the model 1, our estimate on the mean is actually pretty much the same as the MLE of the traditional method. But the point is, I think, is the uncertainty on the actual estimate. So you can see the traditional one seems to suggest that the uncertainty is very, very small. So they're basically saying this is a pretty accurate estimate, but like in terms of Bayesian like inference, the actual posterior distribution is like massively wide. And so yeah, I think that's something interesting to think about. But yeah, thank you very much.
Hey, thank you, David. We've been asking a lot of questions along the way, but if anyone has more questions, you're welcome to ask.
Well, Renee,
Hi,
I was in and out a little bit. I just heard you say something will make me happy, but I didn't catch
Oh.
that. So what would make me
He's-
happy? I want to hear that.
Yeah.
Sorry about that.
He's done two things that will make you very happy, Charlie. So
I was
first of all,
multitasking today.
David, if you can go to that slide where you had the what is that thing? The what is that? What function is that?
Oh, you mean here?
No. Yeah, that one. FFM. What is that thing called? For that 1/1 plus exponential
Oh,
form.
is this the completeness fraction? Yeah.
Yeah, so he's using the completeness fraction as part of the detection process as part of the model. So he's building the detection process into the model, which is something that you keep telling us to do with flares.
Right, but you keep telling me this might be too simplistic. Is that
No, I'm saying that I
Fine.
don't know how I couldn't do it. I can't do it because we don't have access to the process. But David has knows what the process is, and he's calibrated it through injecting fake sources.
Okay, that is great indeed. But David, is this empirically? It looks like a logistic. Is this empirically?
Yes, I can show you. I can
Yeah.
show you a plot. Like it's
Let-
nearly perfect fit.
Oh, so this is actually, so there is so you mean there is physics reasons? Do you have theory to back up this particular choice? Other than being fitted well.
Yeah, it is in general fitted very well.
I
I can show you the plot. Yeah, so this is the completeness factor.
I see.
Yeah.
So Vinay, can we do that?
Not for flares, at least not for what we have been using the flare data for, but for the new wavelet / CNN thing, yes, we can.
Okay. Well, we were doing it more or less trying to find an empirical function, kind of a satisfy the thing. But that's what I was asking. But it seems like this has more than empirical convenience. It has some real physics reason behind it. Is that right?
Yeah, I think like that's generally how, because like this is generally determined by the telescopes. So I mean, yeah, like in general, like that's I guess in terms of telescope, there isn't really like a pure physical reason, but like that's just like empirically how telescope will behave, I guess.
Okay.
Yeah.
All right. That's a good enough reason for me. So yes. Okay, that's indeed a great. What's the other thing? You said there are couple of things. Oh,
those are the two things that were tied together.
Okay.
So the fact that there's this TSM is included as part of the model.
Yeah, explicitly. Yeah,
explicitly. Right.
Okay, wonderful. Thank you.
That does make you happy, right?
Yes. Oh, absolutely. Well, compared to what we were doing, right? Yes. No, I mean, we always want to do something. I just feel it's very a bit ad hoc, right? It's always, so great.
Any other questions or comments? Okay. Actually, can you bring up the last few slides that you had? The last slide that you had with the
yes.
The table. That's right. So you got the uncertainties very. Let's see, how does it go? So I guess for the model too, because shouldn't it be smaller? Shouldn't the uncertainties be smaller because you're imposing additional structure on the thing because you're forcing the GCLF to be the same for all cases.
You mean for N1?
Yeah.
Yeah, I think I think in this case, that might have something to do with like the actual value over here, because it's much fainter than the when you assuming like it's about half a magnitude fainter, and so I think that gets the entire distribution for N1 just gets like extremely skewed to the right, I guess in this case. Yeah, like it gets stretched to 80. This is about, yeah, not so much. So yeah, I think like in general, like you can see the just general the measurement 20-ish, I think. Yeah, I think like the actual distribution in terms of the width, it's not that much of a different. But the actual thing is like this measurement at 20-ish, and this measurement is 15-ish. So what happened is that you can see from this two plots. So the first UDG, the measured mean of the GCLF is about 26, but this one is like half a magnitude fainter. So that means like what that's basically is saying, because the detection limit, that completeness fraction, is always fixed. So what happened over here is basically saying, oh, there's more globular cluster being removed under this GCLF, and then your measurement just gets stretched onto the bigger side. If that makes sense.
Yeah. Okay.
Yeah.
Yeah.
I have another question. So these are the results based on the data. I'm just wondering if you were you done any simulations where.
Yeah, that's what I wanted to do. Like I've done some like simulation, like it's in statistician style, but like it's not realistic at all. So like
that's what I was just thinking, you know, can you simulate the realistic?
Yeah, that's what we've
of
been,
the clusters. Yeah.
Yeah, that's what we've been thinking, because like we're definitely going to have to do some simulation, like because that's the only way to do any comparison, because we need a ground. And the thing is, like what we wanted to do was to there's something called this Python package called ArtPop. So it's basically a package that you can simulate like very like realistic like global like galaxy with like stellar population, and then like GC population, and then from a pure physical model, and then you can simulate that galaxy and then put that into a real image. So what we want to do is to do that, and then like carry out the entire data reduction step and all that on that simulated data, and then do the model fitting. But like we're still figuring that out. So,
yes, this is, you know, Gwen was showing nice simulations of the galaxy with globular clusters and distributions of those. So that's like the physics. So yes, it would be nice, you know, you have your own model on those simulated evolutionary stages, which would be interesting to see what happens, right? In this, I guess Gwen's galaxy was more like the standard spiral Milky Way type, not ultra-diffuse type of galaxy. Right. The one she was showing at the conference just 2 days ago. So.
Yeah. But the one that we're going to use is probably something else. Like we're going to simulate like UDGs actually.
Yeah. You have to do something else than apply your model.
Yeah.
So
but
is it
also,
easier or hard? Sorry, go ahead, Annette.
No, I was just thinking, you know, you're applying this to UDF's galaxies, this ultra-diffuse ones, but is there a reason not to apply it to the regular spiral galaxies, local universe galaxies?
Yeah, you could, but I think it's just like, no, yeah, this is not just restricted to UDGs. Like you could, I'm pretty sure you could apply it to dwarfs and stuff, but I guess for spirals, it's a little bit, because the modeling is probably a little bit more difficult per se.
Oh, yeah, you have different environment, right? You were talking about different environment.
Yeah, because like I'm not exactly sure if the GC system in spiral is actually a surface, because these are pretty much like for elliptical stuff.
Well, even in spiral, you know, globular clusters are more in this kind of this bulge, not in the disk, right?
Yeah.
Isn't it a surface in the Milky Way too? I mean, I thought
Yeah, always, because the central light is usually the sausage profile.
Yeah.
Yeah, that part should translate, but
yeah. Not in the arms, it's only the star sort of bulge type of image.
The halo effect.
The halo and bulge. Yeah. Not the spiral arm.
But I think like the big issue with our current method right now, this is like a shortcoming, which is like I would expect, because I never tested, but I like my hunch is like telling me this model is going to have a hard time if we want to do something like this for like really super massive giant ellipticals, because in those situations, this TSM, this thinning probability, cannot be decomposed like this, and mostly because of this like completeness fraction. Because right now we're just assuming this completeness fraction just depends on the magnitude, but in those like really bright environment, like super giant ellipticals, this thing could also depend on the location S, and that would just bring a whole lot of problem, because that then you will go from like a integration in 1D going into 2D, so the computation is going to be really problematic. And the thing is, like, we don't really know exactly how this function behave when you include the location. So that basically means like these two parameter A and M0, they basically will have to depend on the location as well. And I don't think there really is that big of a that much like literature going on like determining what those are, because like I think what people have done so far is basically, like, for example, for giant elliptical galaxy, they basically just draw like a bunch of annuli around the center, and then for brighter parts, they fit this model once, like little fainter parts, they fit it twice, and then just show like a bunch of logistic curve. But the thing is, there isn't really a continuous modeling of the entire thing. So like
we face this problem when we're trying to do log and log-S type things in X-ray images, and the way that we handle this FFM is characterize it by two things. One is of course M, and the other factor would be the local background.
Yeah, that's basically the location, right? So that's basically
well, no, not location exactly, but just when we construct the FFM, it's actually a function of M and a background value, which is universally estimated. But when you apply it, it's locally in the model, it's sort of I guess you could call it a hierarchical step up. So you get the background locally, and then you read off from this table, which is it's. But yes, it's still a massive computational problem.
It is problematic, and I don't know if this is going to work out. And also, like, there's already a pretty big computational problem because this thing has to be computed numerically. There's no analytical formula, and you cannot really do you cannot really put this integral as a step in the MCMC. So you actually have to compute this thing like directly for each X. And so, but it's still like doable at the moment. But if you include the location, then that's going to be a massive problem. Yeah.
Okay. Any other questions, comments? Okay, so yes, so wonderful. So we, like I told you, David, prepare for half an hour. It extends to an hour.
Yeah.
And that's so. Thank you again. This was a very fascinating talk.
Thank you.
And I guess we'll see you again in JSM. And
yep.
There are a lot of follow-up things that I think we want to discuss with you over there. So we should find a time to meet.
Yeah, of course. Be happy to.
Right.
Looking forward to that as well. Yep.
Let me stop recording here.